recording this a little bit late. So perhaps, goodness, there's only 3 of you now because okay. So Mr. Raj, Mr. Raymond, and Mrs. Tihani, I believe you are the only 3 left. Would either of you like to describe this line? Perhaps Mr. Raj.
Sir, it goes straight up vertically. It does, and the x-axis, it does not change.
Very good. And what is our x-intercept?
3.
3? Okay, perfect. Our x-intercept is 3. And we know that the line goes straight up and down, right? So guide me through doing the slope, Mr. Raj. What is the slope equation? Mr. Raj, what's the slope equation?
I'm not sure, sir.
That's fine. Mr. Raj, it is right here if you need to write it in your notes. Are you good, Mr. Raj?
Yes, sir.
Okay. So the slope equation is the change in y over the change in x. So, Mr. Raj, what is the, let's say, because it is a vertical line, let's go to this point right here. This point would be 3, -1. So let's say, or no, not that one. Let's do this point right here of 3, 1. So the y changed by 1. How much did the x change by?
The x changed by 0, sir.
Perfect. So the x changed by 0. So if this is our slope, then that means our equation is y equals 1 over 0 x plus, well, it's not really important. Y equals 0, x is equal to 0. Okay. So tell me, what do we know about the, does anything stand out to you with this equation?
Could you repeat it, sir? Repeat the question.
What stands out to you about this equation? If there's nothing, it's perfectly fine. So there is something very important about this, what we just did. So the way we write a standard equation is y equals mx plus b. Now, this is important right here, that when you write a standard equation, you must have the y-intercept in the equation. But because this is a vertical line and we said that it has no y-intercept, this equation cannot be written. And we can see this because of what we just did. We found the slope to be 1 over 0. Can anybody tell me what is 1 over 0?
It's 1.
Is it? Um,
Oh, no, sir. Sorry. It's not. It's going to be 0.
That's perfectly fine. Okay. I don't know if you guys have went over this before. Let's do this quickly. So, what we know about a number, about a real number, is that we can write it as a fraction. So let's say that this is a fraction. We don't know what this is because we cannot calculate this in our head. Because if we did, goodness. We didn't learn this on our times table for a reason. So per 0 in our standard division equation 1, we would have to write a number up here, or I don't want to put a circle there because it looks like 0. We want to put a number here that 0 multiplied by this number can subtract from 1, but any number times 0 equals itself. So we are stuck with a remainder of 1 from dividing by 1. The issue is that we would have to try and think about describing this by seeing how normal numbers behave. So let's start with 1 over 1. We know that 1 over 1 is equal to 1 because 1 divided by itself is 1. We can get closer to 0 by making this denominator smaller. Because if you make the denominator smaller, then it will be closer to this fraction of 1 over 0. So let's have 1 over 1/2. Can someone tell me what this would equal? Mr. Raymond. I should have asked, does anybody have any questions about what we just talked about? Okay. If you guys understand what we're doing, then can somebody tell me what 1 divided by 1/2 is? Perhaps Mr. Raj?
0.5.
1 divided by 1/2 is 1 over 0.5. Misty Honey, that is correct what you said. This is 1 divided by 0.5. The answer will not be 0.5. We need to find out what this would equal. Have you guys, you guys should be used to fractions by now, yes? So if you guys do not remember, take down this example. When we divide by a fraction, in our example 1 over 1 over 2, we have to take the 1 and then you're multiplying it by flipping over the fraction in the bottom, 2 over 1. Because if you compare this to 1 over 1, if the denominator is smaller, then the number must be bigger. And the way that we can see that is if the denominator is half as small, then the total number must be twice as big. So instead of 1 over 1, 1 over a half will equal 2. Does that make sense? Because the denominator is half as small, the answer will be twice as big. Mr. Raymond, your network is unstable as well. I don't know if there's a storm or something going on today, somewhere near Guyana. If there is, then that might be the reason why the network is going up and my network is good. Okay, Mr. Raymond, you can just listen. Mrs. Tihani, Mr. Raj, does this make sense?
Yes, sir.
Okay.
Yes, sir.
Okay, so that means that our answer over here is 2, right? So
Yes, sir.
yes. So this is not this yet. For the purpose of this, of trying to find this out, we will need to use a function to find out what this is. So what we're going to do is that we are going to keep on trying to plug in smaller and smaller numbers into the denominator so that we can find out what it would look like at 0. So for the purposes of finding this, we will be applying a function of 1 over x, because this will describe all of the smaller numbers between 1 and 0. So let's erase this. And instead of saying that each of these ticks is 1, we will say that each of these ticks is 1/2, 1/3, 1/4, 1/8, and 1/16. Just for the purpose of demonstrating this concept. Now, because of what we saw about plugging a fraction into the denominator, we can see that because it is 1 divided by a numerator of 1, that means that the answer should be the denominator's denominator. Does that make sense?
Yes, sir.
Okay, so such as we divided 1 by 1/2, since 2 is in the denominator's denominator, the answer was 2. So if we expand this idea to our values over here, our fraction will start at 2, then it will go to 3, then it will go to 4, then it will go to 8, and then it'll go to 16. And it will go forever. So in total, just ignore the y-axis. Let's say this was 1, then the equation will end up looking like this. Does that make sense on the function?
Yes, sir.
Okay, because as the denominator gets bigger and bigger, because we can count in the denominator infinite numbers, so 1 million, 1 billion, and 1 trillion in the denominator, the number, the y value will keep on increasing forever. So when we get to the point that the x value equals 0, and if this goes up for forever, what can we determine about what this value might get to? If you don't know, please say. Okay. So if we are trying to get to the point where x is 0 in this equation, and the y value just keeps going up for forever, then that means that whatever 1 over 0 is, it should be almost infinite. Do you guys understand what infinity is?
Yes, sir.
Ms. Tihani?
Yes, sir.
Okay, so for all intents and purposes, let's just say that 1 over 0 is equal to infinity. And because we have this, and because we cannot write the the equation of a vertical line in standard form because it does not have a y-intercept, and we cannot express the slope as a real number because infinity is not a real number. That means that that means that a vertical line is not a function. And the way that we can say this is that if we had a graph and we said, or no, if we said that we collected data, and we said that for every year we determined how many students there were in a school. If we said at year 1 there were let's say 500 students, year 2 there were 1,000 students, and if we said in year 3 that there were 1,500 students and 1,600 students, would that make any sense? Ms. Tihani, would this make any sense?
Yes, sir.
How so?
Well, in other terms, you could say there were 2 separate classes.
No, I mean in one class. If there were in one class and you said that in one class there were 1,500 students, but you also said there are 1,600 students, would this make sense?
I don't think so, sir.
Exactly. This does not make sense because you cannot have both 1,500 students and 1,600 students at the same time because they are different numbers. If we drew this on a graph and we said that we had like a bullet graph or a point graph where we said that 1, 2, 3. At year 1 there was 500 students. Year 2 there was 1,500 students. Year 3 there were both 1,500 and 1,600 students. There cannot be 2 values in the same year at the exact same time. Like, I cannot say that my hand has 5 and 6 fingers on it at the exact same time, because if you look at it, there can only be one correct number, and it's 5. So similarly to that, there cannot be both 1,500 and 1,600 student population in a class at the same time. So because of the way that it is, a vertical line that contains multiple values at the exact same time does not qualify as a function because it is a logical inconsistency. Does that make sense?
Yes, sir.
Yes.
Okay. There will be times when you use very specific equations that have very specific meanings that may act differently than this. It is 155 about. Have you guys worked with graphs that go like this?
No, sir.
No, sir.
Okay. Mr. Raymond, you're back. So before we do this, I want to talk about a little bit about how what happens when you change functions on a graph. But right now it is 155. So I'll just quickly say. What I'm going to talk about next is what happens when you move a line. Well, for now we're using lines. What happens when you move a function up and down, left, right, and when you flip it over the x-axis, the y-axis, and when you inverse a graph. Move that. That's the same. Have you guys worked with any of these before?
I don't think so, sir.
Okay, so you never, okay, perfect. That's what we'll talk about next. And if we have time left over and you still understand, then we can talk about this mess. Okay, so I would like to take a break. Would you like to take it for 5 or 10 minutes? Mr. Raj, 5 or 10?
Anything, sir.
Okay. Mr. Raymond left. We can take a 5-ish minute break. I'll see you guys back at 2:03, I believe. All right?
Okay, sir.
Okay, sir.
Do you have any questions?
No, sir.
None so far.
Okay, perfect. 2:03. took a little longer than a 5-minute break. Is everyone there?
Yes, sir, I'm here.
Ms. Raj, Mr. Raymond, Mrs. Tiani. All right. Perfect. So we just determined that we cannot have a function that is a straight line on a graph because the slope would be something that does not exist, and it is a logical inconsistency for a function to have two values at any one x. However, you may have multiple values for y, and the reason why is because x would we would say that x would represent time in most instances in simple graphs, and y would be our output. So sometimes, let's say we could say, how many fingers do I have at this second? And it would be 5. And then if we were to count by seconds, we would say, how many fingers do I have at this second? 5. And then it would just stay at 5 forever. So we can just say that I constantly have 5 fingers and it wouldn't change. That isn't an inconsistency, as it would be to have multiple values on a single x value, because that would be saying that I would be having 5, or let's say 5 and 6 fingers at the same time, which is not possible. So along with not being allowed to have vertical lines as our function, we cannot have graphs that have any two values at an x location. So a graph like a function like this wouldn't be logically feasible, because from here you have lots of overlapping y values at specific x's. And the way that you would recognize this is because you would incorporate what's called a vertical line test, which basically means that if you can draw a vertical line and it touches the function at multiple places, that means that multiple y values exist on the same x-axis at a certain x value, or y-axis at a certain x value, and it is not qualified as a function. Now, what you can do sometimes is, for example, you can draw a circle on a graph with a certain set of equations, well, with a certain equation. And if you use the vertical line test, this is not a function. However, the circle would qualify as two different functions later on because of how we are going to draw. Well, how we figure out the equation of the circle using arithmetic. So you can have two functions that have the same y value at the same time because they are independent of each other. So let's say you had one graph that represented my left hand and one that represented my right hand. Let's say I chopped off one of my fingers on my right hand. We would say that my hand has 5 fingers for all time if we were to count 5 seconds. my left hand would have 5 fingers for all of those 5 seconds, and my left hand would have 4 fingers for all 5 of those seconds. And because they're independent of each other, it is logically consistent. So we can have two functions that have different y values at the same x, but you cannot have one function that has two different y values at the same x. Any questions?
No, sir.
Perfect. So before we go into this, we need to know what happens when we change a function. So we're still using lines. So the easiest one to deal with is up and down. So when you change an equation up or down, let's use a very easy y equals x function. So with y equals x, it is just a straight diagonal line that for every one that you count x by, the y increases by 1. So if you move the function up, let's say to here, all you did was push it up so that it's at a different place. If you change the place that any of these functions are at, so let's say that instead of the center being here, you have the center at here, it would still be a similar line, just located at a different place. So the slope would stay constant. For up, down, left, and right, because all you're doing is that you're changing the position that the function is in. Does that make sense?
Yes, sir.
Okay. So in terms of arithmetic, with this y and this x, the coefficients of y and x should not change at all. So if we were to move y equals x up 1, what do we know about it? Mrs. Tihani, what are 3 critical pieces of information about a line?
What do you mean by that, sir?
So when we when we had our equations before in a previous activity, and we wanted to draw the line on the graph, what information did we need to find so that we could locate where on the graph the line is and where to draw them?
We needed the y-intercept and the x-intercept.
Okay, so y-intercept and x-intercept. And by extension, slope. So we know that the slope stays constant. It's just that the y-intercept and the x-intercept change because the line is located on a different part of the graph. So what do we know about the y-intercept and x-intercept of y equals x? Perhaps Mr. Raymond?
Sir, can you repeat the question?
What do we know about the y and x-intercept of y equals x?
Sir, whatever y is equal to, it will be the same thing for x. Example,
Well, continue what you were saying. You might be onto something.
sorry, no, it was the same thing.
Okay. So you're onto something close. What when you have a line, the y and the x-intercepts will tell you what the slope is, essentially. As long as it's not at the origin, that is, because at the origin, the y and the x-intercepts are the same. If we had, if we used y equals, well, if we had a different line, let's say through here, the line starts, the y-intercept would be, let's say, -3, and the x-intercept would be 2. We could figure out that if the y-intercept's at -3 and the x-intercept is at 2, we could figure out the slope by saying that the y, we know, changes by 3 when the x gets to 2. The y increases by 3 because these are the points where this is where x is 0 and this is where y is 0. So we can directly compare them. So in a sense, you are correct. But that only applies to when we know the x and y intercepts. In the case of a y equals x equation, you are somewhat right when you say that they'll be the same, that the y and the x intercepts will always have the same magnitude. Do any of you know what a magnitude means, or an absolute value? Okay, no. So what I mean by magnitude is how far away it's from 0. So if you have an integer, integers, or no, it would be real numbers, rational numbers. So if you have a rational number that includes all of positive and negative numbers, saying the magnitude of whatever number we're using will be equally far from 0 if it's positive or negative. So let's say the magnitude of -1 would equal 1 because it is 1 away from 0. So as we can see on this number line, it is equally 1 tick away from 0 as 1 is 1 tick away from 0. Does that make sense? Any
Yes,
questions?
sir.
Yes, sir.
Okay. So a magnitude simply means how far away it is. If we talk about negatives on a graph, let's say that I'm in the center of the graph. I'm at the origin. In a real life example, let's say I'm at the origin and the axes are compass directions. So this is north, this is east, southwest. Let's say that something was 4 meters south of me. So if it was 4 meters south of me, that means that on this graph, it would be at the coordinate of 0, -4. And all the ticks would be in meters. But this only describes my relation to the point that this would basically be behind me in a sense. So saying that it's -4 0, -4 would mean that it's simply south of me. And that's how we describe positions usually with graphs. So like, instead of saying north, south, east, west, you could say that you have up, down, left, and right. You would say that up is positive and right is positive, but you would say left is negative and down is negative. So the purpose of using negatives in this context is so that you can clarify what direction you're talking about. However, if you were to say magnitude, magnitude simply just means how far away it is from the origin. So since this point, whatever it is at -4 y-intercept, that means it is simply 4 meters away from me. So its point would be 0, -4, or that's what quantity we would use in relation to where I am. But the magnitude, meaning the actual distance from me to the thing, is 4 meters. You wouldn't say -4 meters because that doesn't make sense. Any questions? Okay. So if you use arithmetic, you would say that the difference is from where I am to the point would be a difference of -4, or it would just be like the position compared to where I am. You would say that since it is at the point -4, then that means it is 4 away from me. And we do absolute value by drawing little walls like this around our number. And that's an absolute value. So similarly to how I drew it over here. So as we have it, any questions? Okay. So as we have it with a y equals x, because in the slope that y increases equally as much as x, when you count by x, the y goes up by just as much. That means that you can tell what the slope of the line will be based off of where the based off of where the x and y intercepts will be. And you can take the magnitude of the x and y intercepts by before we had -3 and 2. And you could take the magnitude of the x and y intercepts of 3/2 instead of putting instead of the differences, you could just simply put the actual numbers of where the y and x intercepts are. And you can say this is the magnitude of the slope, so 3/2. And based off of this, you can use the context of where each are located at to determine whether or not the slope is going up or if the slope is going down. So if it would be positive or negative. In this instance, the y is negative and the x is positive, so we can tell that the slope must be positive, so it would be 3/2 in this context. Okay. So the way that it goes back and relates to what we were doing before when we were talking about moving the line is that the magnitude of the slope stays the same because the same slope, you're just putting it somewhere else. And we need to find the y-intercept and the x-intercepts to see how this changed our equation. Now, because we moved it up 1, we need to find out what the new x and y intercepts are in relation to the old x and y intercepts. So because the line touches the center of this graph, the center of the graph is 0, 0. So that means the x and y intercepts must be 0 each. And because we know that the x and y intercepts are 0, 0 each, we just need to find out what the new x and y intercepts are. So since the line touched the origin 0, 0, and we moved it up 1, that means that since the origin was to both the x and y intercepts, and we're moving it up 1, so we're adding 1 to y, that means that we can tell that the new y-intercept will be 0, 1, because we move the y-intercept up by 1. And because we did that, we can figure out what the x-intercept is by just by doing our equation. Now that we know what the y-intercept is, we can rewrite our equation in y equals mx plus b. And because we said that the slope is constant because we're only moving the position of the function, then that means the new equation will be y equals x plus 1. Does that make sense?
Yes, sir.
Yes, sir.
Okay. So I want you to notice in this equation that we only write y equals mx plus b. So we only use the slope and we use the y-intercept. We do not use the x-intercept for a reason. The x-intercept can mean a lot of different things depending on the context, but the x-intercept can equal 0 many different times. But the y-intercept is a lot more important because the y-intercept represents our starting value. So going back to before, when we said that the proper way to write the equation is y equals b plus mx, the reason why is because the y-intercept says where you're starting, and the mx describes how much you change it by over time. Any questions? Okay. So that's why we do not include the x-intercept in this equation. And we would find the x-intercept through our equation now that we have the y-intercept. So I want you to realize that the x-intercept isn't as important as the y-intercept in the sense that when we move the function up or down, I need to clean this up a bit. When we move the function up or down, we simply add or subtract to the y-intercept the amount that we move up and down by. Does that make sense? Okay. So going back just a little bit before when we had our vertical line, because the vertical line didn't have a y-intercept, that means that you have something at a certain time, but you didn't start with anything. And that doesn't make sense because you can't just say something just happened from nothing out of nowhere. At this second, I had 5 fingers, but after that, nothing. It just doesn't make sense. So when we move left to right, a function, let's stick with the example we already have. This is when the x-axis becomes a little bit more important. Because if we move, let's say we move the original equation, y equals x, we moved it 1 peg to the left so that its original center on 0, 0, we now know is 0, 1, or 1, 0. We need to use this information to find out what the y-intercept is. So we know our actual equation being like what we started at. Because we need to find y equals mx plus b. So what do we know about an x-intercept? What does it tell us? Mr. Raj. Mrs. Tihani, what's an x-intercept?
The definition of an x-intercept?
Mm-hmm.
Okay, I would say it's the point at which a line meets the x-axis.
Perfect. From now on, instead of saying line, you should start saying function because soon we're going to talk about different kinds of functions.
Okay, sir.
It's not a slight on you, it's just advice. So an x-intercept is when the line touches the x-axis. And at the x-axis, we said originally, it's when the y equals 0. So what we know is that when the y equals 0, x should equal 1. Or in this case, it's -1. Sorry. Okay, so when the y equals 0, x should equal -1. So we know our slope is 1 because the original slope did not change. So we'll say y is 0. We don't know what the y-intercept will be, but we know that the slope is 1 and x will be x will be 1. -1, -1. So all we're left with is the y-intercept. And that's the point of the x-axis in this equation. To find the y-intercept, we know that at this point that that x is -1, the slope is 1, and we know that y equals 0. And that's the point of this whole equation, y equals mx plus b, because if you have the rest of them, it tells you what the rest of it equals. So because we knew what y was, we knew what the slope was, and we knew what x was, we can find out what the y-intercept is by plugging all this together, and we can see that the y-intercept equals 1. Does that make sense?
Yes, sir.
Okay. So the context of moving the position of the function is that It's relative to the y-intercept. That's the only real position that you need to know involving this, because the x-intercept is dependent on the y-intercept in a sense. So moving the function up in this specific instance was the exact same as moving the line to the left by 1, because the slope was the same. So when you move it left or right, you want to solve for the y-intercept. There will be instances where you can actually take a normal equation and you can figure out what it would look like by moving it to the right or the left by stating what the new y-intercept will be. And there will only be one or a few answers that would qualify. And the fact that there would be different answers sometimes would sometimes depend on the next form of moving a function, which is by flipping it. So when I say flip it, I mean to literally flip it over. And there are 3 main ways of doing it that people use. They flip it over the x-axis, the y-axis, and they inverse it. And inversing it means something else specifically. When you flip something over the x-axis, we have our x-axis right here. Similarly to how if we move a position, the position of a function, the slope will stay constant. If you flip it, the x and y intercepts will be constant. So that means the slope changes. So when we do that, we flip over the whole line over the x-axis. If we have our original equation y equals x, and we know that our x and y intercepts are 0, we flip it over, it would look like this. Okay. Yeah. So when we flipped our equation over the x-axis, we can see that instead of, because we know that it starts at the origin the same way that it did before we flipped it over. Well, because we flipped it over, originally at x equals 1, y equaled 1, 2. But now, because we flipped it over, we can see that when x equals 1, y equals -1. We can just observe this. And at x equals 2, y will equal 2. At x equals 2, y will now equal -2. So based on our observations, we can see that the only difference is that the y values that were whatever it were before, the y values are now opposite. So arithmetically, we could say that because you flipped over the x-axis, it's technically flipping the y. or making the y opposite. So taking our original equation, y equals x plus 0, it would be flipping it over the x-axis would be now saying it's negative y equals x plus 0. Now before, when I said that the x-intercepts and the y-intercepts stay constant, this varies sometimes depending on what you're doing. So I didn't mean to say that they always stay constant. Sorry. I meant to say that the x-intercept will stay constant when you flip over the x-axis, and the y-intercept will stay constant when you flip over the y-axis. The reason why is because when you flip the function over onto the bottom, if you flip it over the x-axis and the x-axis is the middle of it, that means that the x-axis doesn't change. How do I describe this? It would be like saying you had the center of a tire, or sure, why not, a tire. No, a tire wouldn't work either. Ugh. No, I want to say more like a fan. If you have a fan and you had it upright and then you were to flip it over, so it would be like this. You flipped it over the y-intercept, so this part is down, but the center is in the same spot. That's what I'm trying to get across, in a sense. I don't have like a good tool to show it with here. But essentially, because you flip it over, the x-intercept will stay the same. So the y-axis, so arithmetically, you would be making the y negative, and you would do out the equation where it would be y equals negative x minus 0. If we did this with another equation that was more meaningful, y equals x plus 1, this is a better visualization of what happens. We start at here. If we're going to flip this over, we flip it like that, then that means the new y-intercept will be at -1, and the slope would flip over. So the x-intercept will stay the same, but the y-intercept will change. If we look at the slope equation, we still count normally by x because we didn't change the x-axis at all. We changed the y-axis. So we flip over the y. That means the slope will now be opposite of what it was originally. So that's what we did. That's what we did in this instance. And the x-intercept stays the same, but the y-intercept flips over from what it was. Does this make sense? Is there any questions? Any questions? No?
No, sir.
Okay. I just want to make sure that you guys are understanding this. So let's, so when you flip over the x-axis, the y becomes negative. Because the y is now opposite of what it was. And the slope becomes negative. If we did for the, if we flipped it over x, that means instead of going this from top to bottom, how do we do it? Because we're now flipping over the y-axis. How do we flip over the y? Mr. Raj, how did we originally flip over the x? Are you there? Mr. Raj seems to not be able to hear me. Mrs. Tihani, how did we originally flip over the x-axis?
The x-axis, sir?
Yeah, we originally flipped over the
We
x-axis,
do
right?
it. Yeah.
Okay, so if we flipped over it like this, how do we flip over the y-axis? So from x, we went top to bottom. How would y
I
go?
think from y we'll go from side to side.
From side to side. Okay, perfect. So left to right or right to left, however you want to do it. So because last time we said that we don't change the x-axis when we flip top to bottom, this time, since we're flipping over the y-axis and we're going side to side, that means that the y-axis doesn't change this time. So our y-intercept will stay the same, as we said from here. So our new equation or our new function will look like this. So now because our we flipped over the y-axis, our new x-intercept should be what?
Our new x-intercept will be the one, positive one.
Perfect. So our new x-intercept will be at +1. So similarly to how the y becomes negative, the x will become negative. So let's look at the slope equation again. The slope equation is the difference of the y over the difference of the x. So for every y, so we're counting every y for every x. Now that x is, now that we flipped over x, we're counting backwards by x essentially. We're counting backwards from how we did before, because counting forward here is the same as counting backwards here. So because the x in the slope equation is negative, the slope becomes opposite too. So opposed to how we changed the original equation by, let's use the new equation. Instead of making it from how y equals x plus 1 went to negative y equals y x plus 1, so the new y-intercept was negative 1, this time we are simply saying y is equal to negative x plus 1. And the purpose of multiplying the negative to the other side here was so we can get the function into a standard equation. Because the y is isolated already, the equation is already standard. So we leave it as y equals negative x plus 1. So the y-intercept stays the same, but the slope is opposite again. So I'm going to quickly go over what inverse means. So when we inverse an equation, we're not flipping it over in the sense of how we are making the x and y opposite. Let's go back to our regular equation of y equals x plus 1. Clean up a bit. When we inverse a function, we are technically flipping it over y equals x. And the reason why we're flipping it over y equals x is because to inverse something means to, it's not quite to take the opposite of it, because the opposite of this will be flipping it over the x-axis. Taking the inverse of it would be the equivalent of switching around the y and the x. So if you understand the meaning to invert, or if something is inverted, they're not opposite per se. They're just like backwards in a sense. So the new equation will be x equals y plus 1. And that's what it will be to flip it over this line. This is arithmetically how you would do it. And I wouldn't suggest necessarily visualizing flipping it over as you could do with flipping over the x and the y, as much as doing it arithmetically first and then writing your equation, because sometimes it can not make sense. So when we switch the x and the y like this, we need to go back to standard notation, and it will turn into y equals x minus 1. So in this situation, when we flipped it over, it now looks like this line. Now, when you inverse something, the slope does not remain constant. The slope always changes for everything, no matter what you do, except in this specific instance, because if you are flipping it over, y equals x has the same slope as y equals x plus 1. And if you just move it around. So this is arithmetically what happens. You can see that the y-intercept and the x-intercept both became opposite of what they were originally. So instead of y at 1, you have y at -1, and instead of x at -1, you have x at 1. And this changes because you switch the y and the x. So it's not that they become opposite, it's that they've become what the other one was. We can better visualize this with, let's say, the opposite of this equation. If we use y equals negative x plus 1. So if we flip it, if we invert this equation, y equals negative x plus 1, it is now x equals negative y, because this is just a coefficient of x, plus 1. And when we solve it into standard form, it will come out to y equals negative. It will come out to y equals negative x. Okay. So the reason why so we can see that when you inverse it, it will become the same function again because you flipped the line over, but the line was already perpendicular of the invert. Tell you what, it would take me it would take me a little bit longer to explain the inverse today, so we can save the inverse for next time, and you can just we can leave off with what we've already had with moving the position and flipping it over the x and y axes. Do you guys understand everything that we did today? Mr. Raj, Mrs. Tihani, Mr. Raymond?
Yes, sir.
Yes, sir.
Okay. Do you have any questions?
No.
Okay. Today I was a little bit more dictative than usual. We didn't do many activities today necessarily. So I want to make sure you guys understand everything. So you guys understood everything well?
Yes, sir.
Okay, I need to make sure. So just focus today on moving the position of the function and flipping the function instead of the inverse right now. We'll go over the inverse next week. If everybody who watched the recording feels confident that they understood this. And for those people in the recording, if you have questions, please ask in the WhatsApp, and I'll do my best to answer them. Thank you for the 3 of you who are left who didn't have too much connection issues. If you don't have anything, any more questions or things to say, have a good weekend and stay safe.
You too, sir. Bye-bye.
Thank you. Mr. Raj, Mr. Raymond. Okay, Mr. Raj. Thank you, Mr. Raj. Okay. Have a good weekend to you guys in the recording as well.